3, 2, 1. All right, so the next type of series that we're going to talk about is perhaps the most important series in all of chapter 9. It's an alternating series, okay? And an alternating series is appropriately named because it's a series whose terms alternate signs consecutively. So plus, minus, or minus, plus, minus, plus. It has to alternate consecutively. So if you have a series that's like plus, plus, minus, minus, plus, plus, minus, minus, that's not an alternating series. Okay, it has to consistently alternate from one to the other. And they're pretty easy to recognize when you have the rule because you'll see an alternator, which we've already kind of talked about. -1 to the n plus 1 is an alternator. -1 to the n minus 1 is an alternator. -1 to the n is also an alternator. Okay, and what is the sneaky alternator that we talked about? Cosine of pi n, multiples of pi. Multiples of pi. Okay, you could also do sine multiples of pi halves, but it's not as convenient because multiples of pi is just 0 plus multiples of pi instead of pi halves plus multiples of pi. So we don't typically use sine, it's ugly. But cosine of pi n also is an alternator. So that's the sneaky one. It's also pretty easy to recognize when you have the series listed out because obviously you're going to see the signs change, plus, minus, or minus, plus, minus, plus, either one. Okay. Now, alternating series are important because they show up in the rest of the sections. And in fact, the last thing in chapter 9 involves alternating series because there is an error bound. So as we saw in the warm-up, the only series right now for which we can find the exact value of the sum is a geometric series. Okay, if it converges, we have that formula. But there are some other series where we can get an approximation of the sum. And we can determine what's called an error bound. Like the sum is going to be within this interval. I don't know exactly what it is, but I know it's not going to be outside this interval. Alternating series is one of those. Whatever. Just don't make a mess. Remember, custodians are a sacred commodity. All right, so here's the alternating series test. Ready? If we have a rule of sequence or an nth term, a sub n that's greater than 0, okay? We have a positive rule of sequence. Don't distract. Don't pull attention away. Don't compete with the math. Then the alternating series that has the alternator in it times that positive rule of sequence. In other words, we isolate the alternator that only contributes to the sign from the other part. Then if these two things happen, the alternating series converges by the alternating series test, okay? If the limit as n goes to infinity of the rule of sequence is 0, right? We kind of check that anyway, don't we? When we do the nth term test, the alternating series test, if the terms go to 0 and the terms are decreasing past some point, okay? They don't have to be decreasing like from the get-go. They can actually go up a little bit and then get lower. So as long as the terms eventually go to 0, and as long as the terms are eventually decreasing, okay? Does that make sense? The terms eventually go to 0, and the terms are eventually decreasing. Now, I know what you're thinking. If the terms are decreasing, don't they always go to 0? Not necessarily. I'll show you an example where they're not decreasing, but they still go to 0, okay? But those two things, goes to 0 and the terms are decreasing past some point. Then the series converges. Then the series converges, okay? Now notice that this is a one-way test. If you want to write it on there, this is a one-way test. Another one-way test. Not two-way test like geometric and P. If either one of these two things are not met, we don't say it diverges by the alternating series test. This is only a test for convergence if those two are met. So let me show you. Let's just try this out. Determine whether the following series converge or diverge. Okay, so we have an infinite series. The rule of sequence of the nth term is given to us. It's nice. Do you spy an alternator? I spy an alternator. Okay, there it is. Now remember, just because it's -1 to a power doesn't mean it's an alternator. If it were -1 to the 2n or -1 to the 2n plus 1, that's not an alternator. When in doubt, just try it out for a couple of values of n, right? When n is 1, I get squared, which is positive. When n is 2, it's an odd, so it's negative. When n is 3, it's positive. So it's, yeah, okay, so it is an alternator. So here's what we look at. We look at everything that's left after we take the alternator now. And we look at these two questions. Number one, what's the limit as n goes to infinity of n over 2n minus 1? Is it 0? It's 1. Oh, crapola. Okay, that's 1 over 2. Sorry, 1 over 2. Yeah, 1. I was looking at the numerator. It's 1 over 2. It's 1 over 2. Hey, is that 0? No. So because it's not 0, do we say this series diverges by the alternating series test? No, we don't. We don't. Okay, we don't. We say it diverges by the what? The nth term test. Yeah, this one diverges by the nth term test. So right out of the gate, instead of giving you one that works, they give you one that doesn't work. Yeah, we didn't have to even look at the second part. We didn't even get to part 2. Yes, the alternating series test requires both of those things. Now, 99 times out of 100, if the terms go to 0, they're going to be decreasing, okay, consecutively. But there's that one time out of 100 where they're going to give you an example where it's not. But if it doesn't pass both of them, there's no chance of it converging by the alternating series test. But there could be another test that we use. In this case, the nth term test. Okay, the terms don't go to 0; they go to plus or minus 1/2, right? And that's, it doesn't, the alternator doesn't matter because it's plus 1/2 or minus 1/2. Neither one of which is 0. Does that make sense? Okay, cool. So got that out of the way. It's only a test for convergence. All right, let's look at this fella. I spy an alternator. Do you? Yes, it's an infinite series. So we look at what's left and we answer those two, ask those two questions, right? What's the limit as n goes to infinity of n over the natural log of 2n? Who grows faster, top or bottom? The bottom grows faster? No, it don't. No. Natural logs, remember, are the slowest growing functions that grow at all. So the top grows faster. So what is this going to be approaching? Infinity. Is infinity 0? Ah, no. So this series also, let's call it capital A. So A diverges again by what? Alternating series test? I lost the recording. That stinks. I know, right in the middle. Yeah, so look at the next one. I gave you 2 in a row where the alternating series did not give you convergence. What? They're both by the nth term test. Yeah. I'm trying to reconnect. Okay, look at 3. Look at C. Sorry. Look at C. I'll just talk you through C. Do you spy an alternator? Not the usual alternator, but you got Senor Sneaky, right? Senor Sneaky. Senor Salta's primo. All right, so circle what's left. Okay, good. Circle what's left. Get rid of the alternator, cosine of pi n, and what's left? You get 1 over n. What do we do? Number 1, what's the limit as n goes to infinity of 1 over n? It's still recording. Oh, maybe I salvaged it. It does go to 0. It does go to 0. This goes to 0. So now we move on to number 2. Is 1 over n decreasing past some point for some n? Yeah, right. 1 over 1 is 1. 1 over 2 is a half, a third, a fourth, a fifth, a sixth, a seventh, an eighth. Yeah. 1 over n is decreasing for all n greater than or equal to 1, right? It's always getting smaller. The top is always a 1, and if the bottom gets bigger, the whole fraction gets smaller. So it's decreasing to 0. That's essentially what we need it to do. We need it to be decreasing forever to 0. Does this one decrease to 0? Yes. So by the alternating series test, which I'm going to abbreviate today as AST, comma, let's come back up here and call this what? Let's call it B for bend delay. So by the alternating series test, B converges. Now, let me talk about this idea. If I just look at this series from n equals 1 to infinity of 1 over n, let's call this guy C. Okay. What do we know about this series by itself? It diverges, right? This is your harmonic series, your divergent harmonic series. Okay, the terms do decrease to 0, but they don't go to 0 fast enough. The p-value is 1. Anything that's 1 or smaller, it doesn't go to the x-axis fast enough to converge. But look what we're doing. By adding an alternator in there, this is really an alternator times the harmonic series. I'll replace that BP later during lunch. That means the water's out. Okay, yeah. I'll open it. So what does this mean? This means that if I simply subtract every other term instead of adding every term, it makes the sum small enough for it to actually what? Converge. Yeah. So this is your alternating series with a subtractor guy's help. Hey, you want to converge? Well, what if I went through and took out every other number? You're like, well, that'd be great. That would make me small. And maybe small enough to converge, indeed small enough to converge. So this rule of sequence, or this whole series B, converges only under the condition that we have an alternator there, under the condition that we subtract every other term. But without the alternator, it's going to diverge. So yeah. So if we list out these terms here, 1 over n, when n equals 1, we get 1 plus a half plus a third plus a fourth plus dot, 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 right? But because the alternator's there, let's put B on the other side. This is B. If I started listing out these terms, what's the first term? Positive or negative? Well, cosine of pi is what? -1. So my first term is -1 over 1, so -1. And now when n is 2, it's going to be cosine of 2 pi, which is +1. So now it's plus 1 over half. And then it's going to be -1/3. And then it's going to be plus 1/4, dot, 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 plus dot, dot, dot. So that's what I mean. I mean that we're subtracting every other term instead of adding it. That makes the sum sufficiently small to converge. All right. We're going to get to this definition more formally later, but we call this conditionally convergent. Conditionally, there we go. Convergent. It converges under the requirement that there's an alternator. Without the alternator, it doesn't converge. So we would say it does not converge absolutely, like absolute value. If we got rid of the alternator, it diverges. So it does not converge absolutely. It converges conditionally. Okay. Can we figure out to what does it converge? Not really. No. We could take like a sequence of partial sums if we had a calculator, right? And see, but there's no formula for the sum. We just know converges to something, right? To something. All right. So far, so good. Let's look at letter D. -1 to the n minus 1. Do you see an alternator? I sure do. So what's left when we get rid of the alternator? 1 over n factorial. Number 1. What's the limit as n goes to infinity of 1 over n factorial? Oh, that's big time 0, right? Number 2. Is 1 over n factorial decreasing? Yes, it's going to decrease for all n greater than or equal to 1. Most of the time, again, 99 times out of 100, if you answer 0 on number 1, you can just state this on number 2. 99 times out of 100. Okay. Therefore, so let's call this guy ABC. Let's call him, let's see. How about big E? Not to be accused from sigma. So big E does what? converges by the alternating series test. Yeah, by the alternating series test. Now, going off to the side here, what if I look at just the series, call it F, from n equals 1 to infinity of just 1 over n factorial? In other words, what if that is my starting point? Do you see an alternator in this one? No, there's no alternator. So I can't use the alternating series test. But using your intuition, do you think that this one converges? Yeah, it big time converges. Big time converges. We'll prove it later by using what's called the ratio test. But right now, our intuition is like, man, if like 1 over n to the 1.001 converges, then 1 over n factorial converges, because n factorial goes faster than exponential. So it does converge. So this one converges with the alternator, which makes the sum smaller, and it converges without the alternator. It doesn't really need the help, but thanks, I'll let you come along, right? Right. Just take your little kid to work day. He's not really helping, but you know, he's coming along. Yeah, I don't need you, but it's nice to have you around. We say that this one then, E is absolutely convergent. And we don't use that just like for emphasis. Like, are you positive that it converges? Absolutely, I'm positive it's convergent. We mean positive, absolutely. We mean if all the terms were positive instead of alternating, it's going to still converge. Absolutely convergent versus your conditionally convergent. All right, you try this one. You try this one. Letter E, you try. Convergent, divergent. Bless you. Bless you.
I mean, it is a coin flip. It is right. Yeah. I mean, theoretically, it is a coin flip because there's only two options. You can choose. So it doesn't. 50% on the AP test. You're not wrong. This is a 1%. Yeah, that's at least a 4.
Right. Good. Good. That's why this was here. Okay. Let's take a look at it. First of all, I spy an alternator, right? So if you want to just like mentally disregard it, or if you want to circle what's left, or you can actually physically rewrite it like off to the side like this. This is what we focus on now. So you ask these two questions, and it helps to number them. Number one, is the limit as n goes to infinity of that 0? Yes, right? Because there's a constant in the top and it's a quadratic in the bottom. So it is going to go to 0. Does it decrease for all n greater than 1? Not necessarily. So if you look at what n minus 5 squared plus 1, the denominator is, if you were to graph that, that would be a parabola with a vertex at 5, 1. Yes? As long as the denominator is getting bigger, the entire things are decreasing, right? But my denominator for positive values of n It's not getting bigger the whole time, right? Here's n equals 0. Here's n equals 1, 2, 3, 4. So for the first 4 values of n, the denominator is actually getting smaller, which is making the ratios bigger. But what happens after we get past the vertex? Once we get past 5, now forever and ever, those values are getting bigger. And so the ratios are getting smaller. And that's what I heard Landon emphasize. It doesn't have to decrease perpetually forever and ever and ever. It just has to be non-increasing. It could be stagnant too, past some point. And we call that point K. You don't have to really worry about the notation. Just after a while, it starts to decrease forever. It doesn't have to be from the beginning. So yes, this one does go to 0. This does decrease. You're not even going to have to really specify that value. You could say for all n greater than 5 or greater than or equal to 5 if you wanted to. That's good. It decreases. Yeah, I would say it decreases at some point. Yeah, that's good. That's good enough. Okay. Therefore, so Q converges by the alternating series test. All right. So again, if you want to just realize that if that's any polynomial in the bottom, it could even be n to the first. It could be linear, right? Which would be harmonic. The same thing is going to be true. You can have a cubic or a quartic, blah blah blah, but it's going to eventually past some point. Polynomials always have n behavior. Yeah.
So we could either write at some point or for all n that's greater than or equal to 5.
Right. That would be more specific. Yeah. And in fact, the buzzword that you're going to get credit for on a free response is just saying that this thing decreases. If you forget to leave off at some point at this level, you're not going to get docked. Now, if you were coming up with a PhD in math and you left that off, you would get docked. Yeah. Well, it has to be non-increasing. So we can actually include 5 because that's the starting point. Yeah. Yeah. Okay. So there you go. That's a good one. All right. Look at letter F. It's exactly the same as this one up here, right? Almost. I do see an alternator, -1 to the n plus 1. If you take what's left, you get 1 over n. 1 over n is your divergent harmonic series, but does that go to 0? Check. Does it decrease past a certain point? Yeah. Yes. So this one here, we'll call this one big F. F converges by the AST. Now, if you answer it first and it's a free response, you would have to say since, number 1, the limit as n goes to infinity of 1 over n equals 0, and number 2, 1 over n decreases. You could just say decreases. Okay, that's fine. If you want to say for all n greater than or equal to 1, that's true. Okay, that's an optional thing. So this is another conditionally convergent alternating series. Now, is it equal to the one up above? Right, it alternates alternatively. Yeah, this time when you plug in a 1, you're squaring it first. So this one is 1 minus a half plus a third minus a fourth. So it's a little bit different. The sum's going to be a little bit different. It's going to actually be a positive number instead of a negative number. Sums can be negative. That's what B was. It started with a -1, so it's going to be a negative sum. Okay. They're both conditionally convergent. Very good. You got the alternating series test down, right? Pretty easy to spot, hopefully. Let me give you this other one real quickly here. What if I do this one? The sum from n equals 0 to infinity. What if I have like -2/3 to the n? Is this an alternating series? Well, let's see. If you list it, you get 1 for the first term, right? And then you plug in a 1 and you get -2/3, and then you plug in a 2 and you get +4/9, and you plug in a 3 and you get -8/27. Is this an alternating series? Boy, howdy, it's an alternating series, right? So, wow, can we use the alternating series test? Yeah, number 1, the limit as n goes to infinity of negative 2/3, sorry, to the nth. Does that go to 0? Does it go to 0? Remember, we're looking at integer, we're looking at natural numbers. So n is like 1, 2, 3, 4, 5. It's not 1/2, right? If it was 1/2, we'd have the square root of a negative. So it does. It actually approaches 0. Think about what 2/3 would do from above. This is doing it from below. Okay. The only difference is we're looking at values like this. So there's a value, there's a value, there's a value, there's a value. Okay. So this would be like n equals 1, n equals 2. Yeah. So are they going to 0? Yeah, they're just approaching 0 from underneath. No big deal. And then number 2, are the terms decreasing? The magnitudes decrease, but do the terms decrease? No. Oh, crap. They don't decrease, right? They continue to jump, right? Because sign matters now. You have a positive term, which is big, and the next one is negative, so that decreased. But now from a negative, I went back up to a positive, which is bigger and negative. So these are not decreasing. These are not decreasing. So even though it is an alternating series, and we meet the first requirement, is the test conclusive to determine that it actually converges? No, no. But, right, you have to actually look at the terms, the signs of the terms. Yeah, or is that right? Let's go back to what Mason said. I'm analyzing the function with the alternator in there. What do we have to do to use the alternator? We got to take the alternator out. Yeah. So, there you go. So this one, you can rewrite it as -1 to the n times 2/3 to the n. Now you're cooking. See, whatever form you use, you have to be able to write it in that specific form. So you want to separate the magnitude generating part from just the sign changing part. And now if we want to use the alternating series test, I look at just the positive piece. Remember up here that said that it had to be positive? Okay, so now I think I can answer those two questions affirmatively, right? Number 1, the limit as n goes to infinity of 2/3 to the n. That does go to 0, and that it goes to 0 from above. So we weren't wrong to say this. That's not untrue. This is still a true statement. But we got hung up on the next part, okay? Because we weren't doing the test right. Now, is 2/3 to the n decreasing? Yes, it is decreasing. So this series, which we'll give it a name for A for awesome. So A converges by the alternating series test. Now, is there another test we could have used? It sure looks exponential, doesn't it? What's geometric? Isn't that also a geometric series? Oh yeah, it sure is. So you could also do it this way. The absolute value of R is positive 2/3, right? Which is less than 1. So A converges by the geometric series test. Which one is correct? Both of them. Now, here's the deal. If you have to find the actual value of the sum, the alternating series test doesn't give you a way to find the sum, but the geometric series does. So that might help if you had to find the sum. And I was surprised on our warm-up, one of the answer choices was not diverges. You can expect in today's day and age, it'll say, what is the sum? You'll have a number, a number, a number for A, B, and C, and choice D will say diverges, okay? So if you ever have to find the sum, then it's got to be geometric. And so let's see what it's going to be. The sum is actually going to equal the first term, which is 1 all over 1 minus -2/3. Right? We only take the absolute value of R when we're testing it. It has to be negative in the bottom. Okay. And then you'll have your sum. What does it end up being? 3, 5, 3/5? 3, 4, 5, 5/3. The reciprocal of 5/3 is 3/5. Yeah. So there you go. There you go. It's fun. It's easy. It's fun easy. It's fun easy. Now, the last thing about alternating, we've already talked about it. Let me just run through this right here. I introduced it to you early because I wanted to be able to run through this. This is a theorem. If the absolute value of a series converges, that means if you recognize it as an alternator and you get rid of the alternating piece only, like on that geometric we just did, we had to rewrite it. If it converges absolutely without the alternator, we say it's absolutely convergent. Okay. In other words, if the absolute value converges, then the original one also converges, because the only thing that this one's going to be either equal to or less than, right? I'm sorry, this is going to be this way. The one that has the alternator in it is going to be either the same or smaller. And what did we already say in the comparison? If something converges, then anything smaller will converge. Having negative terms only makes some smaller. Remember that. Okay. Otherwise, if it needs the alternator, we say it's conditionally convergent. And we've already seen 2 prime examples, right? These are both your conditionally convergent harmonic series. Very, very important. Very, very important. So what would you say? What would you say about, let's look at these right here. We want to determine if they're conditionally convergent or absolutely convergent. Okay. You see an alternator? I spy an alternator. Now you could do one of two ways. You can either test it for absolute convergence first and say, if it converges absolutely, then it's going to converge in its original format. Or you can get rid of the alternator and do the alternating series test and see if it converges without the alternator, and then see if it converges without it. It's up to you. Okay. I would think look for absolute convergence first. Okay. So number one, let's just redefine this guy to be without the alternator, 1 over the square root of n, which is n to the 1/2. And what do we know about this guy without the alternator? We'll call this guy A, we'll call this guy B. Does this guy converge? No, this is your divergent P series with P equal to 1/2, which is less than or equal to 1. So is this guy going to be absolutely convergent? No, he's not going to be absolutely convergent. Can he still converge under the condition that the alternator is intact? Yes. Okay. So number 2, let's go ahead and do the alternating series test. We'll say, is the limit as n goes to infinity of 1 over the square root of n, does it go to 0? Yes. Okay. And then number 2, is 1 over the square root of n decreasing? Yes, it is. So pretty much for the same reason as the divergent harmonic series or the conditionally convergent harmonic series, this is the same. So so A, the original one, converges conditionally by the alternating series test. In other words, just because it doesn't converge absolutely, don't throw the baby out with the bathwater, right? Keep the baby, get rid of the bathwater. Try it again, right? Maybe he still can converge. There's still hope, in the presence of the alternator. What about this guy? You see the alternator? Yeah, let's go ahead and first look for absolute convergence. We'll redefine this. We'll call this guy A. We'll call this guy B. So to test for absolute convergence, you just redefine the function like that. And then you look on its own merits now without the alternator. Does that guy converge? What does your intuition tell you? Yes. So if this were a multiple choice question, it's exponential in the bottom, boom, it's going to converge without the alternator. So because it converges without the alternator, it converges with the alternator, right? Because all the alternator will do is make the sum smaller. So if this were a multiple choice question, you could just say that one converges absolutely. But if you had to prove it, that's another thing, right? It's like, oh, why do we got to do all this work? Well, now you would rewrite this as 1/3 to the n, right? Which, so B converges by the geometric series test, right? Absolute value of R equals 1/3, which is less than 1. And so what does that mean? So A converges what? What's the word we use? Absolutely. Yeah. Since B on its own merit converged by whatever test, now A, the original function, also converges. It converges absolutely. We don't need no stinking alternator. I mean, if you want to come along, you can. It's nice having your kids around you. I was fortunate enough to teach both my son and my daughter. And I asked my daughter on FaceTime the other day, what's cosecant of 5 pi thirds? And she said, Dad, I need money. And I'm like, dang. And I'm like, I'll give you money if you tell me cosecant of 5 pi thirds. She was getting angry. And she was holding out, not just to make me angry. She was holding out because guess what? She doesn't know what cosecant of 5 pi thirds are. So we had a little lesson. We had a little FaceTime lesson. Hank, what was the right answer? No. Well, almost. I mean, you're in the ballpark there. All right. So tomorrow we'll talk about the alternating series remainder, which is also called an error bound. And I'm going to push to finish tomorrow. Okay. I'm going to push to finish. All right. Y'all have a great super duper rest of your day. It's -2 square root of 3 over 3. Yeah.